So this year, we would like to try something new at CAETS 2020. Before we hear the opinions of the celebrated speakers and panelists, we would like to start by learning what non-engineers think of smart energy networks, and then answering their various questions with the speeches and discussions that will follow. The topic of session 1 is the smart energy network. As we are currently realizing the increasing importance of innovative and sustainable energy solutions, we would like to use this time to talk about the ways in which we could minimize energy loss and protect system safety through methods like emerging energy storage systems, renewable energy, and new IT technology. Now we'll hear from a non-engineer who will open the first session. This opening speech signals the beginning of the symposium. Our first speaker is Ms. Ashleigh Edwards from Johns Hopkins University. Ashleigh, please tell us about yourself and then share your thoughts on the smart energy networks.
Hello, my name is Ashleigh Edwards. I'm 18 and I was born in a small town called Charleston in a small state called West Virginia. I'm currently a student at Johns Hopkins University, and I'm happy to be here today to give you a little piece of what it's like to be a Generation Z student in the COVID-19 era. So I grew up in a place built on dirty energy. When I woke up in the morning, if I walked outside and I ran my hand across the grass, if I looked back up at it, it would come back black. See, there was a coal train that ran past my house, and the powder from the dust of the coal would fall on the grass every morning. And as I got older, though the coal trains stopped coming, the world didn't seem to change as quickly as I expected. Instead, reports of the effects of global warming continued to grow. Whether it was a derecho in 2013 that knocked out power to half of my state, or the fires that burn every year in California. Global warming is not affecting the future, it's affecting my generations now. And though coal, an industry that sustained my forefathers, was the basis of my community, it threatens the future of my generation, of the generation that comes after us, that of your kids, that of your nieces, your nephews, and just humans that come after you. However, in order to change this, well, there'll be a lot of things that have to change. But humans are used to this. Humans are resilient. From the first spark of electricity to the Industrial Revolution, from the automobile age to the nuclear arms race to the smart age, here we are again facing a period of change. And now I know my generation is open to it. However, as a student, I noticed that hopefully your generation, the one that's already experienced so many changes, can be open to one more great change. So, as a young adult, looking out towards what is a very indescribable future, we don't know which direction it will go in, I look towards it with hope because of the people sitting out in front of me, the scientists, the intellectuals, the engineers. You guys are the ones who can help us. And so, as I look out and I see more Teslas and electric cars going down the street, as I see wind farms popping up in the mountains in my home state, and as I see solar panels speckling the roofs as I look out at a city, I notice the winds of change blowing through society. So I have a simple question for you guys that has a very complex answer. How will you do your part to save my generation's future? How will you do your part to give the world a future worth living? Thank you.
Thank you, Ashleigh, for your excellent speech.
Thank you.
You did a good job.
Thanks.
Well, I strongly feel that my generation should apologize to your generation and your children's generation. And we should act now to solve the problem you just raised.
For sure.
Okay, and we have to endow you with a healthier earth and healthier society. Okay. What type of subject or the major are you interested in at Johns Hopkins?
So currently, I'm an international studies and economics major with a double minor in Korean and Mandarin Chinese.
Okay. Well, good luck to your future.
Thank you.
Okay. Good job. Well, Ashleigh just raised the important question, but how can we do that, and what we have to do as a start? The problem we created is very complex, and there is no panacea or one cure-all solution to this problem, and that is why the Korean Academy of Engineering chose this year's CAETS 2020 theme of the conference as Engineering a Smart World, a Smart Society. Although we created the problem, just Ashleigh mentioned, we also created technologies that can cure them. So with this in mind, I'll try to moderate the first session of today, Smart Energy Network. Good afternoon, or good morning, or good evening, ladies and gentlemen. I am Chin-Ho Park, CAETS Energy Committee Chair. Today, I invited 6 esteemed experts to session number 1, 3 speakers and 3 panelists. Let me start this session by introducing the first speaker of today, Mr. Sunguk Justin Moon. He is the Senior Vice President and Head of Enterprise New Business Division of Korea Telecom. Thanks to his expertise in strategy and latest technologies, ranging from smart energy, 5G, smart factory and smart city, B2B turned out to be a core competence of KT. Mr. Moon served over 15 years at NTT Docomo, Japan, before joining the KT. He completed his MBA from Wharton School and has BS and MS degrees in electronics engineering from Waseda University. Today, he will talk about KT's vision for smart energy network. He is joining from recording. Let's welcome him with a big applause.
Hi, I'm Sunguk Moon, Senior Vice President and Head of Enterprise New Business Division in KT. First, I'd like to show you sincere gratitude for providing me an opportunity to introduce an insight over the KT's vision for smart energy network. I will start with how KT became an energy service operator, show you what KT has accomplished, and conclude with our vision to develop it further. As cities become more complex, more issues are stemming from urban environment in the area of energy, security, mobility, etc. We now need to think about what kind of technology can be applied to city. Now let's look at ICT technology in smart energy network. Integration of the leading technology for the fourth industrial revolution, including AI, IoT, cloud, big data, mobile, and security. These became a critical element to implement smart energy network. Acceleration of the convergence of this technology can lead to energy digital transformation and open innovation, which in turn explores untapped new market and unanticipated opportunities. Now let me tell you how KT as a telco became an energy service operator. KT spends almost $300 billion per year as electricity cost, with the highest energy consumption level in private sector. We have this internal need to reduce energy costs by combining our DNA coming from telco as well as our key ICT technology. KT also operates energy network infra and expertise personnel nationwide, who monitor over 17,000 sites 24/7 in real time. KT as a digital transformation frontier is leading a paradigm shift with the integrated energy management platform. KTMAC with AI engine embedded in it. We already implemented digital transformation in various industries, and the representative examples is in energy. Now I'd like to share our use case to show how KT utilizes ICT technology and smart energy platform to enhance energy efficiency and thus reduce energy costs. This case is about a hospital located in southern Korea with up to 75% of energy savings. Simply installing the system at a client side saves energy cost by 10 to 20%. By replacing facilities, saves another 20%. And with ESS and optimized automatic control provided by KTMAC Center, the number goes up to 75%. Next case is about energy management service for franchise and small business, including stores or shops. We simply installed the IoT sensors, controllers, and gateway at the client side, and based on the data sent to our energy management platform, we monitored energy facilities and provided optimal schedule and control to franchise stores. Unlike the prior case, this does not include facility replacement. Savings were reached to 20% in average. And this simply shows how much value KTMAC can create. The last case is about our in-house consulting tool and O&M service. KT Sales Manager can access to the consulting tool called ePlanner using their mobile app and make a proposal for the PV and EV project with the feasibility outcome right up at the client side. We also lined up the O&M service, which provides real-time monitoring and failure response to clients. From the pre-consulting tool to O&M service, we streamlined the service ranging the entire value chain to promptly meet the needs of clients as well as the market. Next, I'd like to show you KT's achievement in energy business. KT has jumped into the energy business since 2015 and operates energy business in the field of PV, energy efficiency, fuel cell, electric vehicle, etc. KT has implemented over 900 renewable energy projects, constructed over 6,000 EV charging stations, and managed the demand response resources up to 1 gigawatt, equal to the size of one nuclear power plant. We have a remarkable achievement for past 5 years, with increased sales by 14 times and monitoring sites by 10 times. As a result, KT has acknowledged with its innovative energy service and platform and awarded Korea Energy Prize in Energy Efficiency for 3 consecutive years and also other various awards, including MWC. Now I'd like to introduce 2 our key technology, which has been an enabler to our achievements. KTMAC is the intelligent energy management platform optimizing the entire value chain from production and consumption to transaction. We are in a progress of developing and advancing our platform to make another progress, since KTMAC is essential technology to move toward energy trade and BPP operator. We have 3 major strategies to develop our platform. We want to convert it to open platform to extend our customer target. Customize our business model so that it can be promptly accommodated by the platform and transform and converge services by applying the new technology. The next key technology is AI-based big data analytics engine called e-brain. From diagnosis to forecast and optimal control, e-brain does far more than just energy management. In the same energy context, e-brain uses real-time data and CAETS machine learning to automatically predict production and consumption pattern, which in turn maximizes the efficiency of energy level and provide even preventive control. With these key functions embraced by e-brain, it can take business opportunities to infinity and beyond. Lastly, I'd like to address CAETS' vision for smart energy network. Our next milestone is to become an intelligent virtual power plant operator that provides energy generation, transaction, consumption services without owning an actual power plant or grid. VPP operator provides integrated control based on digital twin technology and aggregates energy resources on a generation and consumption level to operate virtual microgrid. CAETS will continue to provide our customers with innovative services based on our ICT strengths in AI, big data, and security, and keep creating a new paradigm in energy. In conclusion, when people talk about smart energy, it simply refers to renewable energy, but they are not real smart energy. Energy projects in most cases consist of construction or replacement of hardware, but in real smart energy network, data opening and sharing in real time based on AI and data analytics should be accompanied. As you might know, Korea's energy market is in closed structure. With changes in government policy to open up the energy market, active creation of new business and ecosystem can be followed. Data opening coupled with changes in government policy will help us live another better and smart world. CAETS will keep providing people technology and cherishing people's lives by doing so. I hope I gave you a glimpse of what CAETS has done as an energy service operator, and love to have another opportunity to discuss more details in near term. Thank you so much for your attention.
Well, thank you, Mr. Moon, for your excellent talk. The CAETS developed so-called KMAG and eBrain, and they tried to open their business unit from conventional IT technology to energy service technology and business. And as I give you a short introduction, when Thomas Edison invented the electricity in the beginning, there was no central grid. There's no power plant. So they only had a small microgrid. Now this history is pushing us to go back to the microgrid, and the CAETS is one of the leading companies in Korea trying to achieve that goal. Let me introduce the second speaker of today. He's from Japan, Dr. Ayumu Morita. He's currently working at the Power and Industrial Development Research Institute in Hitach Research Laboratory. He has led R&D in the fields of electrical power and energy as the Director of Energy Innovation Center. Since 2018, he has been engaged in developing and implementing R&D strategies. Dr. Morita is a member of the Institute of Electrical Engineers of Japan and IEEE. He completed his PhD in electrical engineering from University of Tokyo. He will introduce to us Hitach's R&D activities for smart grid. Dr. Morita.
Thank you very much, Professor Park.
준비됐기시마스.
Okay.
Please go ahead.
Okay. Thank you very much, Professor Park. Good afternoon, good evening, and good morning, everyone. I am Ayumu Morita, from R&D Group Hitachi Limited in Japan. It is my great pleasure to participate and make a presentation in this honorable symposium. Today, in my presentation, I would like to introduce our activities regarding the smart grid. Okay, I'm sorry. So first, I will briefly introduce our company, Hitachi. Hitachi was founded in 1910 as a repairing company for the copper mining company Kuhara. So in those days, they utilized US and European electric equipment as transformers and motors, but they struggled with the frequent machine troubles. So the founder, Mr. Odaira, decided to produce the equipment by themselves. This is the origin of Hitachi, and we mark the 110th year anniversary this year. Our mission has not changed since the birth. Contribute to society through original products and services empowered by technology. So Hitachi cherishes the technology, and the founder, Mr. Odaira, was also engaged in the first general manager of the R&D group. Hitachi is a kind of the conglomerate companies. Our major advantage is that we have both OT, operational technology, and IT, information technology. We can contribute to improving the society by integration with OT, IT, and products. Hitachi, we set the midterm management plan every 3 years. The goal, 2021 midterm management plan, is to improve the quality of life of humans and add values for customers. We are especially focusing on the 3 values: social values, environmental values, and economic values. This is a common mission of 5 business domains: mobility, smart life, industry, energy, and IT. Lumada, the bottom side, is our IoT platform supporting the business. Lumada means illuminating data of customers to create new values for them. So let me change the topic about the smart grid. In chapter 2, I will explain the joint activity with University of Tokyo. So this slide shows the Society 5.0. That is a concept put through by the Japanese government. It is a human-centric society in which both economic advancement and resolution of social problems are achieved. For example, regarding the energy, we are past the solution, balance, electricity demand increasing, and environmental considerations. The key to its realization is the fusion of cyberspace and the real world. So, therefore, data plays an important role in the Society 5.0. Aiming to realize the Society 5.0, University of Tokyo and Hitachi launched a joint laboratory in 2016. The goal of the laboratory is to create a future vision and propose the solutions for the social issues to the various stakeholders. Currently, we have 2 themes of smart city and energy. In terms of energy, we are focusing the future complex power network systems, which should respond to a large amount deployment of renewables and proceeding the electrification in the consumer side. It is towards the CO2 emission net zero society. So this activity is not limited to us. We periodically discuss with various stakeholders, including government, power companies, T&D operators, and other infrastructure utilities. And also, we hold open forums to show our vision to the public with publishing the proposals. This figure shows the present discussion points in the laboratory. We have 4 items: local communities like a smart city, bulk power systems, systems and policies to realize our vision, and human resource development. Discussion contents about the local communities are fitted well to today's session. In this discussion, each local community should have unique energy values corresponding to the regional characteristics. For example, it would be possible to create a new local industry using surplus energy of renewables. To create, distribute, and trade these values, we should proceed technological innovation and systemic development. In addition, information and data sharing is useful to create new service businesses regarding not only electricity, but also gas, water, ICT, mobility, and other infrastructures. To improve the entire society's energy values, 3E plus S, energy security, economic efficiency, environment and safety, so local community and bulk power systems should coexist to collaborate each other. This our vision, and proposals were picked up in many other activities, and some contents were reflected the legalization. Act on Energy Supply Resilience that was enacted in February this year. In the next chapter, I would like to introduce our actual smart grid projects. This figure shows the overview of our smart energy network projects. We are proceeding various projects around the world which contribute to accumulating knowledge, know-how, and technology. Today, I would like to explain 3 projects, these yellow boxes. First is a Jump Smart Maui project. As you know, Maui Island used to depend highly on the fossil fuel, which is very expensive due to transportation from foreign countries. They have an aggressive goal of renewables deployment, 100% by 2045. And they also proceed the electric vehicle introduction for environmental consideration. It is clear that they would have network problems in such a situation. Balance with demand on the supply, frequency and voltage stability. In this project, we applied virtual power plant, vehicle to grid, vehicle to house, and demand response to solve the network issues. Right figure shows the system architecture. Machine-to-machine network system dealing with micro DMS. DMS is a distribution management system. It controls the EV chargers as well as network components like SBC, batteries, and switches. This slide shows the network stabilization using the EV charging control. Shown in the left side figure, integrated DMS controls the timing of EV chargers to shift the peak demand, which contribute to suppressing the curtailment wind turbine output. The right figure explains the measure to the dark curve using a V2G, control the charging and discharging timing of electric vehicle. Next project is a Kashiwa no Ha project. Kashiwa is a city name and Ha means a leaf of tree. Kashiwa is a suburban city near Tokyo, aiming for a new bed town with three values: environmental symbiosis, healthy longevity, and creation new industry. Right figure shows the power network system. Kashiwa no Ha consists of two blocks, upper side and the bottom side, in this figure, which are connected by the private power line, as well as energy saving by EMS. Resilience is improved using power interchange between blocks. And also in this project, we are trying to enhance the energy saving consciousness of residents using various visualization and advices through the BEMS and HEMS. In addition, incentives are provided in proportional to their effort. Coupon tickets are provided, distributed, available in the town. Last one is a cloud-based advanced EMS and DMS in the Slovenia project from 2016. Slovenia has an active target of renewables deployment of 25% in 2020 this year. And they experienced a wide area blackout in 2014 due to a big chill. Resilience is an important issue for them. We are developing a resilient network system using advanced EMS and DMS. In Slovenia, there are some DNOs, distribution network operators. So cloud-based DMS enables them operate integratedly. This table indicates the major functions of advanced EMS and DMS respectively. And the bottom figure shows the demonstration system in Idoregia. It consists of the many XEMSs. Light view graph shows the peak shift by controlling the multiple XEMS and batteries. This is the last page, which shows the future vision of the grid management. DARMS, Distributed Energy Resource Management System, could be a useful technology for entire optimization of multiple local networks. This figure focuses on electricity, but integration control with other infrastructure will be more important to realize super smart and environmental friendly society, that is a society 5.0. Recently, hydrogen is frequently discussed worldwide. Hydrogen is one of the candidates in this consisting element in grid management, I think. So I will summarize my talk. Through the collaboration with the University of Tokyo, we have discussed the future vision of the network system. As well as vision, we clarify the technical and system challenges to realize our vision. As I explained in the actual projects, one of the key success factors is to propel digitalization, DX. Data disclosure and sharing would become more important. It is a matter of course that suitable disclosure scope considering privacy protection and cybersecurity should be discussed. Finally, we Hitachi will continue to try to create valuable innovations for a brighter future. This is the end. Thank you for your attention.
Well, thank you, Dr. Morita. Please stay online because we'll come back to you after the presentation. We'll have a panel discussion. So please stay online. Thank you so much. Okay. Well, I think he covered wide scope of the problems that we are trying to solve. And just to tell you the status of Korea, right now we have about little more than 50,000 power sources, including small 3 kilowatt PV plants on the rooftop. But if the renewable energy reaches 20% in electricity generation as planned by our government, the number will exceed more than 10 million small systems. So I hope you could understand the scale of problem that the smart energy network has to deal with. And I think he covered the wide aspects of the problems originate from the variable renewable energy sources, which were not existent before, but now coming into our electricity system, and is keep increasing every day. My next, the third speaker of today is from USA, Professor Mohammad Shahidehpour. He's a distinguished professor of electrical and computer engineering at Illinois Institute of Technology. He also has been the principal investigator of $60 million research grant on power system operation and control. His project on perfect power systems has converted the entire IIT campus to an islandable microgrid. He was the recipient of several technical awards, including IEEE Burke Hayes Award, IEEE PES Outstanding Power Engineering Educator Award, to name a few. He's a fellow of IEEE and a member of U.S. National Academy of Engineering. And today he will deliver his speech on microgrids for enhancing the security, reliability, sustainability, resilience, and economics of electric power systems.
Hi, my name is Mohammad Shahidehpour. I'm a professor at Illinois Institute of Technology. I'm also the director for Robert W. Galvin Center for Electricity Innovation. My presentation is on a microgrid for enhancing the security, reliability, sustainability, resilience, and economics of electric power system. I usually start my presentation with a picture of Edison. He was the one who built the first electric power system in the United States back in 1881. And this is the sort of a remnants of that still available in the lower Manhattan. But there were two critical issues that he implemented as part of his project. One was that Edison built a DC power plant. And we are going back to the days of Edison. A lot of generation that we have these days are DC, like a solar PV, and a lot of loads are DC, like your cell phone, your laptop, LED lights. So it's quite reasonable to go back to DC. The second thing that he did, which was very critical, was to build a microgrid, because at that time there were no electricity grids available, and it was a standalone system that he supplied electricity to mostly rich people who could afford electricity at the time. So we're going back to the days of Edison by building microgrids. All the indications point out that in extreme events, and in particular in this time of uncertainties, microgrids can do quite a bit of job for enhancing the power grid operations. Talking about uncertainty, this is the growth in the solar PV in the state of California, which is the 5th largest economy in the world. What you see here is a growth in solar. So the brown area is mostly solar power. There's a significant growth coming up, but it sort of ends into a sort of a duck curve that we call it, which represents the case that this dark brown line shows the net load, which is a thermal load. So during the day when the sun is shining, we don't need much of thermal generation. But at night, when the sun is not available, we need to supply much of the load with thermal resources. So there's a significant ramp here that much of the electric power grid cannot tolerate. The other thing is that we need to have a lot of thermal generation available as reserve in order to be able to supply power at this time. So if somehow we can eliminate this load, the peak, and move it either to here or here, we'll come up with the power generation and a net load that is a lot more flat and much more manageable. The best way to eliminate this is by control of the load and the local load. That's possible by using a microgrid. So let me talk a little bit about the microgrid. This is a model of a microgrid that's connected to the local distribution system. This is a link that connects these two systems. And in case of an emergency, you can open this link and the microgrid will be islanded. And in that case, you can use local generation to supply local load. If you don't have enough generation, you can curtail some of the loads and basically manage the system to satisfy whatever objective you have, whether it's economics, whether it's sustainability, whether it's resilience, whether it's security, whatever the goal is, we can supply that by building this microgrid. So microgrid allows locally integrated renewables and other distributed generation resources to provide reliable power to customers. It provides or protects critical infrastructures from power outages. So if this operation is a hospital, or if it is a police station, or it's a military installation, we make sure that while you're providing local control, you can supply whatever elements in that system that's the most critical to remain energized. For instance, if it's a hospital campus, we make sure that the surgery department, if that's the most critical element, always remains energized. So you can manage the local load in however form you need and whatever objectives you have. So it protects critical infrastructure from power outages in the event of physical or cyber disruptions in the power grid. It ensures that critical operations can be sustained during the prolonged utility power outages. So if this outage of the local power system is prolonged and it lasts, let's say, a week or 2 weeks or a month, during all that time, this microgrid manages the local load as an island system and makes sure that the system remains in operation. So in a sense, what we're talking about is a grid of the grid. We're not talking about eliminating a power system. What we're talking about is to build more of these microgrids in order to make sure that the system, these microgrids, using their own objectives, always remain in operation. One example of this microgrid is the university where I come from. So this is the university operation. We are near the downtown Chicago. You see the downtown, and this is the university campus. It's a small campus. We only have around 42 buildings, but the entire campus is operated as a microgrid. So it has 7 loops that you see. Loop number 1, this is loop number 2, loop number 3, and all these loops are connected either to the north substation or the south substations. South substation and north substations are linked to the local electric power system. In case of an emergency, we can open these ties at these 2 locations, and the entire campus will go into an island mode. So this is the schematic of the microgrid. So the power comes from the utility grid at 12.47 kV. At the substation, it's downgraded to 4,160 volts. And the entire campus is at 4160. So in case of an emergency, we open the switches at these 2 substations. Campus will be in island mode. So these are the 7 loops. Each loop comes with its own generation load. And in case of an emergency, we curtail non-essential loads. We make sure that the system remains in operation. This is a 12 megawatt operation. We saved the university about $1 million a year. And ever since this system has been in operation, which is 2013, we have had no downtime. We have had a number of outages, but the system has never been down. So it's a really great engineering practice that shows how microgrid can save university operations, critical operations in case of an emergency. So this is a wind unit at the campus. This is the solar canopy that supplies electric loads, electric EVs, electric vehicles. So this is about 20 kilowatts of power generation, supplies power to all the utility cars and electric vehicles that we have on campus. Also, we have a tabletop model at the Galvin Center. From here, we demonstrate how the campus is operated. You can see different buildings on the campus, and then we can demonstrate to spectators how the microgrid works. We also have a control room for this microgrid. So this is a control room. These are the monitors that the system operators can monitor this entire system. For instance, this is one of the operations of the campus. Kitting Hall is one of the buildings that we have converted to an nanogrid. So this is the solar power generation. So you can see as the solar power increases, the power that we draw from the grid drops. This shows how much solar PV we have available. This shows the building load that varies throughout the day. So here we collect all the load, and in case of an emergency, we figure out what's the best way to manage the grid. So basically, this is the entire operation of the Galvin Center, which includes the campus microgrid. We have added a lot of components. We've got flywheel, we've got high reliability distribution system, we've got the EV charges, all the campus lights are LEDs. We've got the controls, we've got the nanogrids, and all of that points out that microgrid can be customized. Operation can be customized in order to supply critical loads and satisfy certain objectives. One of the things that we have done as part of this microgrid is to build a multi-microgrid. So here, what you see in the red area is a university microgrid that I just explained. And in the black area is the local distribution system microgrid. So these are two microgrids. University microgrid is 12 megawatt. This one is 10 megawatt. So the total of 22 megawatts of load in this part of Chicago that can be islanded and managed in case of an emergency. So we work with different entities. We work with Quanta, we work with Schneider, SNC Electric, Alstom, Microsoft, OSI Soft, Comet, which is a local utility. All these companies have helped us build this system that can make sure that in case of an emergency, system remains in operation. This part of Chicago is a critical load because the central police station and a number of security buildings and a hospital in this area, and the city wants to make sure that in case of an emergency, system remains in operation. One other issue that I would like to bring up is the emergency operation, how that's done with microgrids. So this is the picture that you see in one of the southern islands in the United States after they had the hurricane. And you see it's quite devastated. And all the indications point out that using a microgrid, you make sure that the critical infrastructures within this local region remains in operation. So in a sense, what we are doing, if you look at the performance of the microgrid as a function of time, here we have the normal operation. Then the system goes through an outage, so you have degradation. Here the system is down, you start repairing it, and you're back to normal. So here, this is the system without a microgrid. So the system is in a normal operation. You go through the degradation, as I pointed out here. The system is an outage. You rebuild the system and back to normal. With using microgrid, we switch from the red line to from the black line to red line. So the red line shows with microgrid. And then as you see, the performance of the system is higher now. The performance is higher, and also the duration is shorter. The duration of the outage before was from this point to this point. Now it has dropped from here to here. So using a microgrid, you can enhance the operation of the system. So with microgrid, you still have the normal operation. You go through the degradation, which is a drop. But the system remains in operation during the outages. So here we had the complete outage. Here we had this partially sustained operation. And then finally we go to normal operation, which is up here. So as you see, microgrid allows you to sustain the critical part of the system even when the larger system is an outage. So we go through different stages. One is robustness. That's before the outage occurs. We build and rebuild the microgrid to make sure that it's robust. It's the responsiveness that makes sure that the system responds to the outage in a cohesive manner. And also system goes through this recovery mode, where we make sure that as we go from here to here, the recovery makes sense and is done in a sort of a professional manner to minimize the outage to the system. So this is the operation of the microgrid in different stages of that shows how the system is managed. Now, we have written quite a bit about this. There are a number of articles that we have that explains how these things work in practice. All you have to do is to go to the Galvin Center website and you can see everything that you need to see. I'd like to finish my presentation by pointing out that basically when you build a microgrid, now whether you use a blockchain or other entities within that, traditionally when we did the electric power system operation, we make sure that all the other infrastructures were available. Water was available, oil was available, natural gas was available, telecommunication was working. But what we have learned is that as you're building this system, you're basically dealing with a quite complicated and interlinked infrastructure. Here, electric power system operation very much depends on the availability of natural gas, availability of the telecommunication system, water, oil, and all of that. So in a sense, when you are looking into the reliability, sustainability, security, economics of electric power system, you have to consider that as a part of a much larger system and make sure that all these elements are in operation in order to make sure that you have a reliable electric power system. And in order to do that, the use of microgrid has demonstrated that it's the best way to do it. Thank you very much.
Well, thank you, Dr. Mohammad. I think he raised the quite important issue of having a microgrid in this ever-changing world. We witnessed recently from a newspaper that in California we had a big fire for a week, lasted for a week, and then the power system went down and the complete state was basically experiencing outage. If they had the microgrid that he just explained to us, then most of the critical places should stay in energized state. That can save many people and many facilities. And also he emphasized the importance of electricity. In Korea, about 19% of the final energy is by electricity, and 81% is something else. But electricity is the brain of our energy system. Like he said, water, gas power, they're all related with electricity. So even though the percentage only is 19%, the importance of electricity is very, very critical. And the having a microgrid with increased renewable energy penetration is a must that we should take part and develop as soon as possible. Thank you again for three esteemed speakers. And now let me introduce three panelists who joined here in person or online live. I invited actually two panelists from the startup company. They're actually running a startup. They founded a startup and they're doing business related with this smart energy network. And I invited one person from the expert who are deeply involved in the policy making for European Union. So first, let me introduce the first panelist, Dr. Jong-Woong John Choe. He's a founder and CEO of Encored Incorporation, located in San Jose, California. He formerly worked as the president of LSIS in Korea. He is also IEC ACTAD international expert and representative of Korea. He raised fandom, in my word, fandom in Korean energy business by his so-called behind-the-meter business model. He's recently appointed as a member of Korea National Energy Committee. Let's welcome Dr. Choe.
Yes, good afternoon. My name is John Choe from Korea. My company is located in San Jose. And the other company, the joint venture with the SoftBank in Japan and the Seoul office together there. In my generation, still very strange, the tele-video conferencing. Today, the one moderator and one panelist in offline here. So that today, the panelists, the speakers are introducing their own company and the technology. So today, I will introduce my technology there in perspective of the generals. Oops. As you know, that because of so many penetration of the distributed energy resource, lessening, the grid, the existing, the current grid must be modernized, and many in using the technology, especially I'm focusing to the AI technology with the energy transition, so that today the distributed energy resource management system, there's the DAMS, is the emerging technology in this session. And the other is that the demand response and the transactive energy, especially the behind the meter. And then so many of the people that are not interesting for the energy data, especially that many people that are understanding the energy data from the metering data. So that the data interval is only the 15 minutes interval data, but now I am gathering, aggregating data in real-time data, in every second data from the power system and power market. And then the three kinds of data. One is the meter data, and the market data, and the grid data. This data must be converged and integrated together for the energy transition and for the power system and the power market. And here the AI strategy that as we can get many values from the energy AI through the algorithm and data and the business models, so that we can have some recognition and the prediction and the automation and interaction and the creation. So that I configured the analytics engine. The one is the predictive, the engagement engine, and the other is the proactive engine. So that combining the advanced energy analyze the deep learning and AI, we help you fully optimize, manage the risks, and maximize your experience. The AI engine, we must take consideration two kinds. The one is the behavioral science, and the other is data science. Behavioral science to find the correlation with big data. And the other, that's data science, to discover the causal relation in data science, so that we can improve some cost, engagement, and efficiency. And then what kind we can have that's what the energy AI does. One is the behavior and the pattern analysis, and the other is the energy usage disaggregation, and the distributed energy, the generation, and the load, the forecast, and the energy optimization, such as the usage and the demand response, and the transactive energy there, and the diagnosis and health monitoring of the equipment, and the power quality, and the volt-var optimizations, such as the power quality, the volt-var optimization, and the conservation voltage reduction. Here, the process to analyze the Encored data analytics is the process of the interpreting the information to make the valuable decisions from the import data, utility late analysis and a model, and optimize, and finally the offer the proposal to customers. And so recently, so many distributed energy resources are located in very diverse location geographically, so that we must always gather the data from the location and the timely data from every location, individual location. So real-time data and AI potentials are being unlocked by the generation of big data and increase the processing power. In the energy sector, the energy AI can enable the fast and intelligent decision making, leading to the increased grid flexibility and the integrate of VRE and the resilience of power system. Finally, I would like to emphasize every electricity services must the response in real time. That, as you know, here, firstly, from the black stat on the power system and the voltage regulation within the several seconds, and the next is the frequency regulation in the minutes interval data. And the third is load following, with some minutes. And finally, the load balancing within some hourly interval data, so that we can have some electric services for the reserves and the regulation and the capacity and some black stat. Thank you for the attention.
Thank you, Dr. Choe. Well, please have a seat. Yeah.
Okay.
We'll come back.
Okay, right.
A little after. Okay, let me introduce the second panelist, joining live from Denmark, Dr. Brian Mathiesen. You're here, right?
Yes.
Okay.
Hello.
He's a professor in energy planning and renewable energy systems at Aalborg University. He's a member of the EU Commission Expert Group on Electricity Interconnection Targets in the EU and the newly found Science Advice for Policy by European Academy's Expert Group on a system approach for the energy transition in Europe. He's also a principal investigator of the Reinvest and S-Energy projects and the program director for Sustainable Cities. So he has a lot of experience in the European policy making, I guess. Let's welcome him, please.
Thank you very much, and thank you for inviting me to speak here at the panel today. Good morning, good afternoon, and good evening, everyone. I will talk about a concept called smart energy systems, a multi-sectoral approach towards 100% renewable energy and decarbonization. I believe we have a number of challenges. We can see that renewable energy has lower and lower investment costs. We can see that the prices of electricity are falling, battery prices are falling, and as a result, we see that system design failure because the merit order of electricity prices is breaking down the system and making it impossible to invest in new backup power plants. We can also see from a system perspective that actually electricity demands are the lowest of the demands. Both transport and heating or cooling are larger demands. When we look at the costs, it's clear that electricity grids are more expensive than thermal gas and liquid fuel grids per capacity. And also we can see that different storages have different costs in different sectors. So the questions we have to ask ourselves are, how do we balance the future energy system? What kind of energy storage do we need? What kind of redesign of our energy systems are needed in order to integrate more renewables and more cheap fossil-free energy? What kind of role do we see for different kinds of energy storages in the future? And how can storages across the sectors be used more cost effectively? Another important point I think we have to ask ourselves are, what kind of role does energy saving have in a system where we also see falling energy prices? So what is the balance between the demand and the supply? Here's an example of how we see things are happening in a lot of places in Europe. This is northern Germany and Denmark, and we can see a huge correlation between the amount of wind penetration and the spot prices. We actually see with 50% wind in our system, we will see a 40% or 50% reduction in the prices. So this is a sign that we need to redesign our system. This is a sign that we cannot continue on this road. Also, it is clear that many of the European countries are planning to actually expand the renewable energy penetration. So we'll see this problem increasing in the future, which is a sign that we need to think about how we can redesign. In a lot of places, I see, not only in Europe, but across the globe, that the strategy to integrate renewables is interconnections and trading. And I believe this is a very dangerous path to go, because in a lot of places we will see a strong correlation with weather patterns across borders. So when you can illustrate it by when you have ripe fruit, then the neighbor will also have ripe fruit and you're not able to sell it. So either you have to sell it really cheap, or you won't be able to sell it at all, the electricity, or nobody will have any electricity, so you have to buy from each other. But the problem is that you have shut down your power plants because the operation time is too little. So I think this is a very dangerous way to go, the strategy one. The second strategy you could choose is the smart grid strategy. And here you tend to focus quite a lot on the electricity system, which in reality is fine, but it's only part of the system. The problem is that you see a lot of focus on smart grids where you only look at batteries or hydrogen, and you look at hydrogen as a solution to put electricity back on the grid, not to choose other problems. And at the same time, we can see that electricity actually in many cases is only a smaller part of the demand. In many cases, it's maybe 25 or 30% of the demand, and the rest is transport or heating in industry or buildings. And this is why we propose a smart energy systems approach instead, where we try to use a lot of the different grids. We use the smart electricity grid to balance the loads and to transport the electricity. And there's no doubt that electricity is the backbone of the system. But we also use thermal grids or district heating grids to balance out the heat demands, because the heat demands have huge peaks, which means that we have to handle this in a very specific way. Otherwise, our system cost, both for the electricity grid for heating and for the power plants that need to operate, will be very expensive. And then we have also the gas grids or the liquid fuel grids that we can use as a major part when we want to decarbonize also heavy-duty transport. Here's an illustration of the problem that we are looking at. If we store electricity in a pumped hydro plant, maybe the price is 125 euros per kilowatt hour. In a Tesla battery, it's around 300 kilowatt hours 300 euros per kilowatt hour. A Tesla Powerwall or equivalent is something I would strongly not recommend in a future energy system, because it's the most expensive way to balance your system. If we compare this to thermal storages, we can have a large pit storage, which is 1 kilowatt hour per 1 euro per kilowatt hour, or a household level storage, which in effect is not very flexible, because when it's cold in all the houses. But here the costs are much lower than the electricity storage. So we see a tendency that thermal is cheaper than electricity, but also bigger is cheaper in both cases. And here's a diagram showing you a comparison across more of these vectors. Electricity storage is about 100 times more expensive than thermal storage, and thermal storage is between 20 and 50 times more expensive than gas storage, and gas storage is about 2 to 5 times more expensive than gas storage. So we have a cascading falling price here, strongly falling price, and of course there's also an efficiency issue. Storing electricity with the purpose of putting it back on the grid is ineffective and should be avoided. Thermal storage has small losses, gas and liquid storage almost no losses. Of course we can't use the electricity stored in a thermal storage, but I believe that we also need to heat our houses and to store and to shower in a 2050 renewable energy system. And that's why I think it's important that we redesign the system so we use these storages between the production and the demand. If we look a bit closer into the buildings, there are many parts of a building that you would have to look at. But some of the things are, of course, the behavior inside the building, is the thermal, and this is where smart meters can help. It's the thermal performance of building. Here, smart meters can also help. But it's also what kind of supply do we need? We have investigated that in my research group and in our research community quite a lot, both in a national and international setting. And it's clear that it's underestimated how much the heating and cooling demand is part of the energy system. Even going to a country like Italy, Spain or Greece, we see very high heating and cooling demands, and of more than 40 or 50%. And when we disaggregate the heating and cooling demand, we also see that even in Greece and Spain, cooling demands are rather small compared to heating. And in all countries, also countries like smaller countries like Cyprus or Malta, we have a higher heating demand than a cooling demand. So we need to not underestimate this. In the European Commission, there's been a lot of work on how to go towards something that meets the Paris Agreement. And 2 years ago, this publication, A Clean Planet for All, came out. And one of the things that we can see in A Clean Planet for All is this development or this wish where we go from a situation today where we use 50 kilowatt hours per square meter on average to a situation where we use around 50 kilowatt hours per square meter. This is, according to the insulation industry, not really possible. So we need to find other solutions here than to insulate and remove half of the energy demand for heating and hot water and cooling in the buildings. One of the ways we have tried to outline here in a project called Heat Roadmap Europe. And what we have done is we have mapped all of the heat demands and surplus heat supplies down to 100 by 100 meter across Europe. And we have used that data to try and create some smart energy systems using our advanced hour-by-hour analysis of the entire energy system, including industry and transport. In doing so, we found some remarkable results. One of the results, which is not really rocket science, but is something that we really need to think about, is illustrated here in the town of Middlesbrough in the UK. Here we have a heat demand of around 10 petajoules per year, and we have an excess heat source in the harbor of about 35 petajoules per year, but they have no district heating to supply the heat of the houses, which means that they use oil and natural gas to heat the houses instead of the excess heat. We can see that all across Europe. And when we map, we see that there's a lot of heat demands all across Europe, and it actually correlates rather well with excess heat demands, but also with new renewable energy sources. In a country like the Netherlands, we can see that they have more excess heat than they have of heat demand in buildings. So there's a lot of potential to have a lot more energy efficiency and to balance the system better. When we look at this, we see that we need to insulate the houses, but maybe not half the demand because it's unrealistic. But if we both decrease the demand on the demand side and also change the supply side, we can see that both of these elements actually create similar levels of energy savings and CO2 savings. If we look at the empirical evidence of what has happened across the European countries, we can see that those countries that have had natural gas and oil boilers as a predominant source, they have literally no or next to no renewable energy in their mix. But if we look at those countries who had district heating, we can see a strong correlation between a higher penetration of renewable energy in the heating sector compared to countries that do not have that. We actually tried to look at each country in Europe to see what do our GIS, our mapping exercise and our energy system analysis exercise show us, and we can see that there's a huge potential for energy efficiency on the heating and cooling side, of course, depending on the typology of the buildings and how closely these are placed together. In countries like Spain and Italy, the potential is very high. In Germany, for example, there's a potential of going towards 50% district heating compared to the 12% today. All across Europe, we believe that it's important to decrease the end demands by 30 to 50%, depending on the country. We should have, in urban areas, we should have district energy networks, and in rural areas, that means in areas where you have no neighbors, you should have a high efficiency water-to-water heat pumps if possible. Another part of the transition is, of course, that the heavy-duty transport. Here we work with a concept called electrofuels. We take the electricity from the electricity grid. We capture carbon either from a carbon source or from gasified biomass or biogas. We make a hydrogenation process where we then able to create methane, methanol, DME, or even jet fuel for planes. This is a viable way to go, and it's also a viable way to introduce the energy storages that I talked about before. So now we have a thermal storage and we have an energy storage in the liquid fuels and gas grids. We have analyzed this in different publications called Smart Energy Europe, where we can see that it's possible to significantly decrease the energy consumption in Europe, and we can also illustrate how different supply systems for heating and for transport means different things for the overall primary energy supply. One of the important things to understand is that not everything that you think is green enough, and not everything that you can do, which you believe to be a good thing, is a good thing when you look at the system perspective. One thing that you will, of course, ask if you look at this going towards 100% renewable energy system is what are the costs? And what we see is that the costs are actually similar to the energy systems that we know today, but that the investment costs are higher and the operation and maintenance costs, of course, are lower. We're looking further into the supply chain effects of energy efficiency in several of our projects. One of the projects is called Synergies here. Thank you for having me on board, and I look forward to the panel debate.
Thank you, Brian. You raised other important issues, in addition to the electricity. You raised the issue on heating, cooling, and gas fuel and liquid fuel. So the energy system is a complicated system, so we have to try to optimize all the sources for the right consumption. Okay, thank you. My last panelist is joining live from Switzerland, Dr. Andreas Ulbig. Okay, I think he's ready. He's
Yes.
a co-founder of ETH spin-off company called the Adaptricity. He's also vice president of Swiss Energy Foundation. He received his PhD degree in engineering cybernetics from the University of Stuttgart. Previous work positions include the R&D department of RTE, the French transmission grid operator, and the International Energy Agency. Let's welcome him with a big applause. Êtes-tu prêt? Ready? Okay.
Yeah, thank you very much. Good morning, or rather good afternoon in Korea. Thanks also from my side for inviting me and for organizing this splendid conference. So as the last panelist, I can kind of wrap up of what happened earlier. My focus is on smart grids and data analytics in smart grids in order to make cities and the environments we live in smarter and better prepared for our well-being and for promoting our well-being. So starting with where we are today. This probably comes not as a surprise for most of you. Today's electricity grids as a whole aren't actually that smart, especially if you go from the high voltage transmission grids, where there is actually a lot of sensor systems and actuators to control and optimize grid operation. As soon as you go down to the distribution grids, and especially to the low voltage grids, there's less and less sensor elements, so less and less data to analyze about the grid status, hence almost no grid transparency. This is for a good reason, because most of the grid infrastructure is actually in the low voltage grids. This is where most of the cables and transformers are actually situated. So digitalizing this part of the distribution or of the grid is more tedious and requires more investments, which for a long time was simply too expensive to do for the potential reward that there would have been there. Now this is changing. Or actually, what happens is that, bringing smartness into the electricity grids, as I said, has been around for the high voltage levels, the transmission grids, for quite a while. Power plant automatization and monitoring, substation monitoring has been around for decades now. And now finally, what we now discuss as the smart grid, the smartness in our cities and residential areas is happening, not only in the form of smart meters by replacing the old mechanical meters, but also by photovoltaic inverters that can measure the grid voltage, the supply of photovoltaic electricity, of course. Now increasingly also charging points for electric cars that can not just monitor what happens in the charging process, but also actively control and manipulate the charging process to provide flexibility to the grid. So this is now happening, and this is in a way the last step of this long progress of making the electricity grid as an infrastructure more intelligent. This is very much needed and appreciated, because nowadays the energy transition does actually happen mostly in the low voltage distribution grids. Surely in Europe, where there are already millions of photovoltaic units in the grid, Germany alone has almost 2 million PV inverters connected in a distributed manner already. Other countries are picking up. Also in the US, trends are going from large wind farms and photovoltaic units that are connected to a higher voltage levels towards local, really distributed installations like rooftop solar photovoltaics, and of course electric cars that are connected to households and not to large installations. So This is now happening, and this is where our startup Adaptricity is very much active. We have been founded as a spin-off of the Swiss Federal Institute of Technology, ETH Zurich, roughly 6 years ago. Now we are mostly active in the German-speaking countries with grid operators there, but also with larger entities like Enel in Italy and E.ON in Eastern Europe as well as Northern Europe. Also in Asia, we have first experiences, notably with China Light and Power, the grid operator of the city of Hong Kong, or at least of large parts of that city. So what we are providing is insights into what particularly the low voltage distribution grid is doing. Here you see an example for a neighborhood in Zurich, where we can monitor, if needed, close to real time of what the status of the grid is. So how voltage bands are evolving, how grid bottlenecks are forming or disappearing due to changes in load and production patterns. And you can see here in the analysis example a bit more in detail that we are able to analyze exactly what's going on the street level in distribution grids, identify faults that are happening, also identify why they are happening, which is even more important, and identify parts of the networks that have a tendency to be at risk in certain conditions. So this way we can also forecast, at least in a rough fashion, which parts of the grid will be most vulnerable to, say, more renewables, more electric heating with heat pumps, or more charging from electric cars in the future. Some examples will follow right away. More on a city level, you see here the city of Basel with roughly 170,000 inhabitants. We were the first to analyze the smart metering data that the city was collecting from its residents. And the grid operator actually tasked us to identify what value this data has. As you can see here, for the purpose of this presentation, some more illustrative examples, you can visualize quite nicely how electricity consumption on the left-hand side for residential customers, but also how electricity production on the right-hand side shown for the photovoltaic units in the city are evolving over time and in space. So here, this allows you to identify where you have demand hotspots as well as production hotspots. You can imagine that this is also possible to do over time. More specifically, you're also able to cluster customers to identify which households are consuming electricity predominantly at what time of the day or at what season of the year. So you can identify temperature-dependent loads, for instance, so air conditioning, which has high consumption in the summer, and heat pumps, which have high electricity consumption in the winter. But what one can also see, or what we experienced, that before you actually get to these nice visualizations and analysis, you have to do a lot of data preparation. So the smart grid and smart grid analytics is also a lot about data preparation, cleaning errors that necessarily happen in real measurement data due to communication faults and other sort of errors. So for this, we use machine learning and AI in order to identify faults and smooth them out with plausible fillings of the data loops that happen. So this also allows you to, if you understand what the situation today is of a grid, allows you to make forecasts of what challenges will arise in the future. For instance, if there will be more electric chargers. We analyzed this here for the city of Lucerne, where for real neighborhoods with the measurement data that the operator had today, we were analyzing what will happen in this grid with more electric mobility. And as you can see, a lot depends on where exactly in the grid you are. So there are certain areas that become relatively quickly orange and red, which means they become overloaded from electric chargers. But it also depends on how this charging happens. If you look to the right side, if you use charging control, you can very well accommodate electric charging while not overloading the grid. Whereas on the left-hand side, you see how the charging patterns without the coordination from the grid operator will impact the grid and make grid operation much more difficult. This is true for electric mobility. And in the case of Switzerland, where there are already a lot of heat pumps, I think, almost 300,000 heat pumps for a country with roughly 8 million inhabitants. That's quite a lot. I think this is one of the benchmarks for the European countries. And you can see that, of course, if you have more electric heating due to the trend to avoid fossil fuels for the heating sector, you will have challenges with the grid, as you can see here. With as soon as the penetration goes around and above 25%, you see certain grid parts that become weaker and will show more influence and impact from electric heating, namely in the form of under voltage events, which needs to be treated with grid upgrades. But with this analysis, a grid operator can identify already now where the future problems will be and can in time already reinforce the grid in the weak spots that have been identified. Well, with that, I'd like to end. Here you see an overview of my team, and I'm looking forward to the panel discussion later on. Thank you very much.
Oh. Thank you. Well, Dr. Choe? Okay. Right now it's 3:24, and I have time until 3:40, so we have about 15-16 minutes for discussion. First, I'll pick up some questions from the audience. The first question goes to Dr. Morita. Are you there?
Yeah.
The question is, do standards exist in vehicles to enable grid control of their charging? Or do you need to use different solutions for different cars? Can you answer this question?
Yeah, basically, regarding the electric vehicle, so now some standardized chargers for each countries. So this is the standard. However, maybe the deployment of the electric vehicle and the fast chargers impacts on the distribution grid. So in case the design, the planning of the distribution grid is important to satisfy with electric vehicles societies.
Mm-hmm.
That's my answer.
Okay. So, Dr. Choe, can you tell us a little bit about the question is about standard?
Yes, that's now there's so many vehicles types that we have, and the charging the type is quite different. So that's as you know that every standard is so late. Mm-hmm. Compared to the market situation. Oh, okay. So that, of course, I am working in the IC standards, but every the standard, so we must more prepare.
Okay, all right. So I think I should understand that it's not ready yet.
Sure.
Okay, all right. Okay, the second question goes to Brian. You're there?
Yes.
Okay.
Yeah.
You mentioned in your slide that the price of electricity is going down and down, getting lower. But many of us, including people in Korea, that European countries, especially with high level of renewable energy, like Denmark or Germany, that the cost for citizen went very, very high. So by showing the graph that decreasing electricity costs, what is your opinion in general? Considering the fact that the electricity price increased maybe 3 times, then yeah. Understand my question.
Thank you for that very important question. Mm-hmm. I think there's a lot of myths going around about the costs of renewable energy. I would like to refer to the facts. The facts are reported very well every year by LASAT, a consulting group who collect all of these data. And what we see is that renewable energy has lower prices than fossil fuels in many cases, especially onshore renewables and large-scale solar PV systems. That's the fact. And with regards to the electricity prices, there's a lot of myths going around about the electricity prices and how this is done. in Denmark, we have had falling electricity prices when you exclude taxes and VAT, and this is excluding the costs of support schemes for renewables. So what we have seen is decreasing prices with increasing renewables. When we actually look at the facts, in Germany, they have not seen the same tendency. This is because they have constructed the feed-in tariff in not a very smart way, which means that they have paid overprices in many cases compared to what we have done in Denmark. But not only what we have done in Denmark, because you also see in the UK, for example, they have an excellent support scheme. It's called the CFA, the cost for difference feed-in tariff, and this has decreased the prices significantly. So I think there's a lot of myths going around. Renewable energy, electricity is cheap. Offshore wind is not cheaper than coal yet, but it will become cheaper than coal very soon. And there's a lot of myths about different countries' tax schemes, which are going to the fiscal budget and not necessarily to the erection of renewable energy.
Oh, okay. You're making very important point. Good answer. Thank you. Well, the short question, I think maybe another question to Brian. Maybe you cannot answer this question, but the question came to me. How do you see the future for cold fusion technology in energy production? Can you answer this question?
Well, we have an ongoing debate about thorium reactors and different kind of future, I would say, future power generation technologies. And we do quite a lot of analysis on this and really monitor how the prices develop. I have worked together with material scientists and physicists on something called solid oxide fuel cells and solid oxide electrolyzer cells. The main challenges we see there are the temperature levels and the coefficients of the temperature coefficients going across the balance of plant in such units. And I see the same in some of these newer technologies. So I think I warmly welcome to research in this. But while people research, I think we need action on the ground with real solutions, known technology. And if these technologies can compete with renewable energy in 2050, when we have to meet the Paris Agreement targets, then I warmly welcome them to compete with renewable energy and energy efficiency.
Oh, yeah. Thank you. Good answer. Well, I have about 9 minutes, so I'll spend this minute for my last question. Gave it to you in advance. My question to all of you is, how could smart energy network contribute to the urban energy system in case of natural disasters such as flood and especially the COVID-19 pandemic? Dr. Morita. I cannot hear you.
I'm in mute. So I agree that the smart energy network contribute to improvement of the resilience, especially resilience of the urban energy system. So as Professor Park mentioned, fire trouble in California. So we also in Japan, we experienced several wide area blackouts due to the natural disasters recently. For example, in 2018, a big earthquake occurred in Hokkaido area, the North Island, which led to island complete blackout, continuing over 10 hours. And also in 2019, last year, so 2 strong typhoons attacked Tokyo area. So in that case, in Chiba Prefecture and neighboring Tokyo, so the number of outage units reached up to 3 million, and with a long recovery duration time of over 10 days. So according to the situation in the METI, so Ministry of Economy, Trade and Industry, so we discussed countermeasures to keep the resilience. Three items have been discussed. So first one is strengthening the bulk power grid by increasing the regional interconnection capacity. So in the scale of the entire country, which enable the power interchange when the shutdown of the power source in some areas, region to region. So this is one. And the second is proceeding the decentralization. That is like the smart city, which can do an islanding operation when stopping the power receiving. So now the reconstruction of the local grid equipped with the renewables, co-generators, and batteries is planned. And last one, that is important. So now we consider the recovery procedure after the blackout. So it is important to determine the recovery system in case of the disaster beforehand. So it increases not only the preparing equipment, but also the systems, recovery system, including the collaboration with the other T&D operators, other infrastructures, utilities, and communities. So anyway, to improve the resilience of the network of the urban city, so I think it is necessary to think measures from the various points of view. That is the answer.
Okay. Thank you. Andreas, can you add something on that?
Yeah, so as an addition, but also as a confirmation what was just said, I think if you have more data of your infrastructure, particularly the electric distribution grid, it is of course easier then to identify and analyze faults that happen from natural disasters faster, and ideally also to better identify them. What I mean with that is to identify exactly, to pinpoint where exactly the fault is, why you have an outage. Usually it's quite easy to know that you have an outage somewhere, but it's more difficult to analyze why you have this outage and what can be done to overcome it very quickly. So for this, real-time measurements from the distribution grid, I think, are very helpful. Also, if you know that certain natural threats like typhoons can happen every year or so, you can use the existing data from the electricity grid to make future scenarios to identify where the potential damage would be or is likely to be. And in this way, you get insights of where you should reinforce your grids. For instance, if you should place substations somewhere else where they are have a lesser risk to be flooded, for instance. Okay. I think this would help. Then in the case of COVID, we have all been in lockdowns more or less throughout the world. I think if you make this data from smart grids available to the operators via a cloud-based service that can also be accessed from home office, this can be very helpful to keep up the daily operations, even if not all employees can go to their physical offices.
Oh, okay. All right. Thank you. Dr. Choe, can you add something on that?
Paradoxically, that we can find that the COVID-19 is making the air clean and the sky blue. So if they are penetrate more and more, it will have a very effective the results in the improving global warming. But I think that it will be very difficult to control and manage rather than the existing centralized power system. Because the power are distributed in various locations geographically. Therefore, based on the IT technology, the systems such as the more automation or the remote, the control and the monitoring with the real-time energy data should be put into energy system. Especially can predict by the predictive and proactive engagement. When a problem occurs, it should be designed to have the quick and automatic resilience.
Okay, Brian, you have 1 minute. Can you add
Okay,
something?
I will do it fast.
Especially
I agree.
talk about some pandemic issue with the smart energy network, please.
Yeah, I think the key here is security of supply. And the key thing is to understand if several things happen at the same time, how robust are our systems. I agree very much to the other panelists' points, but I would like to add that a resilient and robust system in cold or warm climates also require that we consider to have more energy vectors. If you have several energy vectors, you're much less vulnerable to a blackout or some kind of faulty system in the electricity grid. I think Andreas pointed out some very heavy challenges that will occur when we have a lot of heat pumps, for example, together with EVs in our grids. And I think it's possible to handle this. We can have different batteries in the distribution grids. But it would be nice if we had a parallel thermal system, which is also which would also be cheaper. And I think it could create much more robust system in the case that we have several of these events occurring at the same time. The key thing is to get a robust system where we're able to handle these things. And one thing is to handle the electricity system. We have a lot of solutions for that. But a thermal or a gas system, you actually can operate them without electricity for a longer period. And that will create resilience where households and businesses can operate even in a time of several crises occurring at the same time.
Yeah, thank you. About right time. I think I have to close this session by the wrap-up comment. The world that we are trying to solve somehow the problems that Ashleigh mentioned in the beginning of our session. She asked a very simple question, but I think the 6 experts answered in very complex way. I hope she can understand. But I just want to tell you that about 2/3, 67% of CO2 emissions come from energy generation, transport, and energy consumption. It's a report from IEA. And the global consensus on this issue can be summarized in my term in 4 characters. OECD. O stands for optimize, E, electrify, C, capture, and D, decarbonize. I don't have time to explain all those, but the OECD is the consensus that the global community is agreeing. And I can answer the Ashleigh that even though it looks very complicated, but we are trying to develop the technology that can cure the problems that our generation created. So I hope we can still wait for the better world with the smarter engineering technology. I thank you all for joining us today from online and offline. And please enjoy the sessions and startup pitches following this event. Thank you very much.
Thank you to all the participants of session 1, and especially a big thank you to Mr. Park Jin-ho, the session moderator. As mentioned earlier, each session will be followed by IR pitching by 2 startups. So promising companies with outstanding performances were chosen from several candidates. Today, 4 startups will show the world their ingenuity and innovation. The first company to give their IR pitch is Enerwin Korea of South Korea. This company is developing highly efficient, low-cost wind power generators. More details will be shared via video.
Hello everyone. Today I'm very pleased to introduce Smart Symmetrical airfoil blade wind turbine to members of CAETS and everyone participating in this event. On November 5, 2019, more than 10,000 world scientists adopted a joint statement. The climate crisis will lead to a major disaster and urged mankind to act immediately. Now we have to switch to clean and sustainable energy. Enerwin Korea will contribute to creating a clean global environment with innovative clean energy solutions. This is a video of 3 kilowatt and 10 kilowatt wind power generators developed with our new technology. The graph in the lower right corner is based on average data per minute. As you can see, electrical energy is produced even in low wind speeds of 1 to 3 meters per second. This technology will make a big change in our human lives. That means we can produce and use enough electrical energy for our daily lives by using the lower wind speed of less than 4 meters per second that is usually blowing around us. The breakthrough was inspired by the fish's body shape and applied to the wings of wind generator. A key technology is the AI-based wing control system that automatically adjusts the wing's angle within 90 degrees to achieve optimal efficiency. At high wind speed, the wing angle is adjusted to a proper angle in real time to maintain a constant RPM by allowing some winds to flow between the wings. This wind power technology was patented in Korea, Japan, China, and the United States. This technology is patented as a horizontal axis wind generator with symmetrical wings and its wing angle control method. It was selected as the GEP program by the British government in May 2019. Enerwin Korea plans to establish a local subsidiary in the UK during the first half of 2021 to supply the wind turbines to the UK and Europe. A brief summary of this technology is as follows. Number 1. Productivity and economic efficiency. 1.5 times more electrical energy production and faster recovery of investment costs. Number 2. Safety. Active pitch and yaw control. Number 3. Efficiency. 1.5 times more efficient. World first use of symmetrical airfoil blade for wind generators. Number 4. Smart control system, SCADA. The global small wind market size is projected to be USD 1.79 billion in 2025. And the market size is expected to grow 2 to 3 times more when Enerwin's wind power technology is introduced. Enerwin has been preparing for the establishment of local corporations and factories in the UK, and we want to implement these plans in detail to supply Enerwin's wind turbine in the UK and Europe. Business plan consists of a distributed power solution with wind, PV, ESS, and can play an important role in energy self-reliance, especially in areas where it is hard to get electricity, such as islands in Africa. With innovative wind power technology, Enerwin Korea will take the lead in reviving the earth by spreading renewable energy solutions, such as wind and hydropower around the world. Thank you.
Yeah, it was the video by Enerwin Korea of the South Korea. We appreciate a lot for their dedication and contribution to the better society and the world. The next startup introducing itself is Relectrify from Australia. This company deals with batteries and energy storage solutions. Their video will tell you more.
Hi, my name is Valentin, and I'm a co-founder and the CEO at Relectrify. Our mission is making energy storage affordable. Renewable and reliable power benefits significantly from stationary battery storage in homes, industry, and the power grid. However, standard lithium-ion batteries today remain quite expensive and short-lived. Relectrify focuses on 2 problems to address this. The first problem is related to lifetime. Large battery packs contain up to 200 individual series-connected cells, and the weakest cell limits the entire pack. When batteries are brand new, the cells all perform strongly, and therefore none limit the pack. But as battery packs are used, the cells age unevenly, and the lifetime of the pack is limited by the single weakest series cell. The second problem is related to cost. Connecting to homes, industry, and the grid requires an AC output. Since normal battery packs provide a DC output, an expensive inverter is required. We have solved both these problems. Relectrify's mixed software and hardware solution merges the traditional battery management and inverter into one stronger performing, lower cost solution. Every cell is controlled individually, which overcomes the weakest link issue. This increases battery life by up to 30%. Alongside, the cell level control provides a partial AC output, which allows inverter complexity to be vastly reduced. Instead of 20,000 times per second, it only needs to switch about 100 times per second, and largely avoids the need for filtering capacitors or inductors. Our approach results in around 30% less battery management and inverter component cost, which spread across the full battery system leads to about a 10% cost reduction. Our technology also provides fault redundancy and includes sensors collecting battery performance data, which we then use to further improve our algorithms to make the batteries last even longer. Now, taking a step back, this technology opens up two opportunities. The first is allowing new batteries to be cheaper and have a notably longer life. The second is reusing so-called second life batteries, used batteries from electric cars, for a uniquely low capex storage solution. Relectrify was founded in 2015 out of battery research at the University of Melbourne, Australia. Since then, we have scaled our technology across residential and large industrial solutions. These have already found use with Volkswagen Germany, Nissan subsidiary 4R Energy in Japan, and power utility Vector in New Zealand. This January, Relectrify launched our inverter replacing solutions, which are already installed in a project with US power utility AEP and Nissan US in Ohio. Consisting of modular 70 kWh blocks, these solutions suit installs up to multi-megawatt hours. Moving forward, Relectrify is positioned as a cornerstone supplier of battery control technology. Typically, we supply electronics and software to companies that build battery packs, though for high volume opportunities, we're also open to technology licensing. In select cases, Relectrify also offers system prototyping to demonstrate to customers the additional performance that our solutions unlock. Relectrify is actively looking for strategic collaborators globally that either manufacture or install stationary battery packs at significant volume. We would love to connect with any relevant companies to see if Relectrify can help make your battery packs cheaper and longer lasting. Alongside, while Relectrify is currently well capitalized and not raising, if there are investors with interest in a future Series B round, it would be good to connect also. Thank you for your interest, and we look forward to discussing further together.
Relectrify from Australia. We also look forward to find good partners to work with you in the near future. We will now have a 10-minute break, and session 2 will start at 4 p.m. sharp. So now you're free to go out and enjoy your break, and we'll gather here again at 4 p.m.